morning. So before we take up the topic transition metal catalyzed cross coupling, we will actually continue from the previous class, that was on organomagnesium, and one of the applications was in the synthesis of heterocycles, which is again a special kind of, is an important topic which will be talked about after a few classes. But in the last time we gave a reaction called Bartoli reaction, and it's a very useful reaction. If you recall, you have to identify the starting materials. The starting material is nitrobenzene and the other portion is vinyl magnesium bromide. Okay. So, this is the thing, and you do not have to do anything, just mix them, but the ratio of the starting material should be 1:3, that is the minimum, and the product that you are going to get is straightaway and straightaway. So, of course, this has to be hydrogen. So, vinyl magnesium, this straightaway you will get this indole. So, it's a neat reaction. What is the mechanism? The mechanistically, actually there are three different steps. The first steps is a kind of a unique reactions, what often we do not expect. If you look at this nitrobenzene structure, we often write this, then this magnesium adds to the oxygen, and nitrogen charge is neutralized. So, result is you get an oxygen linked vinyl group, nitrogen is now neutralized. This oxygen now is linked with magnesium bromide, fine. Okay. Then what? Then actually this oxygen is picked up by the vinyl Grignard. So, vinyl portion rather, and what you will find? You will find a nitroso compound, and of course, the other portion would come out as oxygen minus, is an enolate, oxygen minus and enolate, it comes out. And so, essentially what you get is a nitrosobenzene in the intermediate. What next? You can expect one more. This is minus that comes out. Then if you have magnesium bromide, and again then the first equivalent is consumed, then the second equivalent, mind it, nitrosobenzene has a unique property though. Many of you probably know it can be used as a Diels-Alder dienophile. The reaction takes place across the nitrogen double bond oxygen. Then if you cleave it, that means you can incorporate nitrogen in an heterocyclic, in an acyclic moiety. Then another reactions very recently is developed by two scientists called Hayashi, one of them, the other is Macmillan. Both are organic chemists specialized in organocatalysis, and if you do an aldol reactions with those with nitrosobenzene, you will see oxygen is getting linked to the carbon, not the nitrogen. Often we are accustomed to polarize this nitroso bond towards this oxygen, right, and nitrogen gets the positive charge, that is just like a carbonyl. But in this case the polarization is in a reverse manner, probably because of the aromatic ring system. So, what we will be getting now is a double bond again, nitrogen and oxygen, then you have now, and you have magnesium up here, magnesium here and this bromide. I think what next, I think all of you probably would anticipate, right? What is the next possible reaction? The way I have written, I think is very apparent, right? It will undergo 3,3 sigmatropic rearrangements. So, this one, okay, I mean well, how do I, okay, 3,3 sigmatropic rearrangement. So, you get a new now carbon carbon bond formation. Nitrogen, magnesium, and then you have this oxygen now, oxygen as a ketone, okay. And then all of us can understand what will happen next, because nitrogen magnesium means polarized towards nitrogen. So, it's like a Schiff's base kind of formation, and eventually what we will get? You will get nitrogen up here, it's a 5-membered ring, and then you have oxygen here magnesiated and this. Then probably the next step is I think this proton transfer, and this is where one more, the last equivalent of magnesium is consumed. That is the reason why 3 equivalent of magnesiums are required. All of us know magnesium also picks up the acidic hydrogen. So, it will pick up this acidic hydrogen, acidic hydrogen, and then this should be polarized, and so eventually you will be getting a dimagnesiated product. This is magnesium bromide up here, and this is O magnesium, and so if you next is if you acidify during the workup, so all of us can guess what would happen. It would produce NH, on the one hand, on the other hand it will have this OH up here, and which I am sure it is not very stable. So, under the reaction conditions it would eliminate water, and it will give this indole. It is a very nice OA, and it is pretty versatile reaction, there are a lot of examples which have been executed by this method, okay. And the only thing that the organomagnesiums reagents are sometimes very reactive towards many functional groups, that is the disadvantage. And next most disadvantage is this use of excess amount of this organomagnesium, okay. And now quickly just see whether you can work out a reaction scheme without Bartoli reaction. For example, suppose you are advised to make a prenylated indole, So, how would you synthesize this? How would you synthesize this? What is the starting point? Obviously, see, the most of us what we do, we will do a retrosynthesis, right? And what are the first step in starting the retrosynthesis? You have to look for some of the transforms. What are the transforms? We have not talked about so far. Towards the end of the course, actually, we will talk about the constructions of the different heterocycles. I mean, so far we have talked about only 2. One of them was oxazole by Van Leusen method. Second one is Bartoli. Okay. So, how other than that, whatever you have studied in BSc. So, what could be the proper, for example, indole synthesis? How many indole synthesis do you know of? How many I said? Not well, I know at least 10. Okay. Now, obviously, the Fischer indole is the first one. The modification of the Fischer is Klinger method, Klingman method. Okay. Third one could be Madelung synthesis, Madelung indole synthesis. Fourth one, Bartoli maybe. Okay. Fifth one, Nenijevsku reaction, very useful reaction. Sixth, I thought I know 10, that is what I am trying to say. Sixth, Gassman synthesis, Paul Gassman indole synthesis. We studied in 1974, Professor Asima Chatterjee taught us, and that was discovered in 1973, she taught us in 1974, I still remember. What else? Okay, so maybe more, maybe plenty. Actually, if you just review this book by Lee on named reactions in heterocyclic chemistry, you will find many more. At the moment, I cannot remember. Oh, in terms of that Fürstner indole synthesis, Fürstner, Alois Fürstner, he is the director of Max Planck Research Institute in Germany. What he has done, he has basically formed the carbon-carbon double bond of the pyrrole ring by McMurray coupling. All of us know McMurray coupling. And then one modification is there where you can form the double bond by Wittig reaction. So now it has already been 8. So 2 more we have to collect. So likewise, we are actually developing one more based on Hauser annulation in our lab. We have already done it, but examples are very few. So hopefully that also would. Then there are other methods. So that means when you are given a problem on synthesis, I mean, of course this retrosynthesis should be done, but one of the major steps is identifying the right transform. That means the forward reactions. Okay. For example, when I asked this question to you, you suggested that Fischer-Indole should be applicable, but believe me, it is not applicable. There is a reason. That means you have to understand the reaction mechanism. What is the key driving force? Key driving force means you have to find out the rate determining steps. It is a multiple steps, but one of the steps should be rate determining step. And Fischer-Indole is very good for many molecules, but it is not appropriate for the very simple molecule like this. That means for simple molecule mean to say that 2,3 dice unsubstituted. There is no substitute. Right, it does not work. So that is the thing. That means you have to know a little bit in the depth of all these transforms, then only you have to choose. So okay, and of course, and other points should be the starting material. So in this case, for your convenience, I suggest, let us say, the starting material is this one. Okay, so that means our retrosynthesis boils down to a benzenoid like this. Now, what is the forward? Forward direction, forward reactions. So what do you do? Let us say I give you the answer. The appropriate starting appropriate transform is Bartoli reaction. So what is the suggested step? Next step. Suzuki coupling with Suzuki coupling, fine, with the corresponding boronic acid, that is fine. So we have to, yes, Suzuki coupling could be a possibility, but there are, okay, so we have to again know all these details though, but how to make the Suzuki boronic acid. For simple one, simple aryl boronic acid, perfectly alright, but it is an unsymmetrical one. So the Suzuki may also takes place on the other side. In most cases though it takes place, but the one that has been worked out is a starting from the organolithium compound actually. So what you do, you make this lithium reagent and lithium reagent. So lithiation can be done by, since you have a bromine already there, so the halogen exchange. And if you do with phenyl lithium, the reaction proceeds in 100% yield, 100% yield. What next? Then you have to introduce this allyl or prenyl group here, Mind it, in most cases the prenylation does not take place unless you put cuprous cyanide, right. But in some cases actually if the reactivity is so compatible, then you can directly do this this displacement, especially if it is an allylic substance, not this simple alkyl substance. So, the product then would be just basically a prenylation, and you have to take note of this thing, that stability of these lithionitrobenzene, because we have seen that many alkyl lithiums also undergo addition to the nitro compounds, but in this particular case it is pretty stable. Probably by controlling the temperature you can stop further reactions of these, and once this is done, then of course the next step is quite easy, right. Next step is very easy. What is that? Vinyl magnesium bromide. So, 3 equivalents of vinyl magnesium bromide, you can straight away go to this material. Okay. So, this is from the last class. Now, now today's topic is cross coupling. Cross coupling is a very important topic, all of us know. In the last year we talked about, I think exclusively rather I should say, talked about this. So, since now you have other people also from other sections, and I have to talk little bit about this. Just so what I will do, I will just give an overview of the cross coupling. Then I will have selected examples from pyrrole. Probably in the next class we will have examples from other classes. Okay. And there are so first of all let us define what is cross coupling. How do you define that? See, whenever you start a topic you have to first you clarify the scope and definitions and the scope. I mean how much we talk about. Okay. So, when I say cross coupling, I think what does it mean? Let us say someone who is bolo, okay. What do you mean by cross coupling from Delhi IIT? Is it taught there?
Carbon bond formation.
Is it taught there?
What's it?
Is it taught in your place? Was it taught?
Yes.
Huh? Who taught that?
D. Bandyopadhyay.
Huh?
Professor D. Bandyopadhyay.
D. Bandyopadhyay, Devbrata. Okay. So, so what is the meaning of cross coupling?
Cross coupling means formation of carbon bond.
No, I will not take it. There are so many carbon bond formation in organic reactions. Huh?
Palladium, mainly catalyzed metal.
Okay.
Not only carbon.
So that means you have to define. When I say cross coupling, what does it imply? Cross coupling of what? Not really. Not really. So, okay. I think I think the best thing would be the organometallic people writes. Have you ever heard of this ligand coupling? If you remember this ligand coupling, they have to tell you what is exactly cross coupling is.
The ligands on the palladium.
Right, and on metals. That means that's it. That's two different ligands on the metal surface undergo coupling. So, it could be it could be of course AR, and it could be this AR. It could be alkene and alkene, right. It could be, I mean all possible combination, aryl and alkene. What else? What are the other possible? Now we know, now our domain is, our scope is heteroaryl, right. We have heteroaryl, aryl. So, I mean you can go on writing so many things. Then heteroaryl and alkenyl. So, alkenyl. So, I mean instead of writing alkene, alkynyl, I write alkynyl. So, you have so many possibilities, but when I say ligand coupling means actually the reaction is taking place on a metal surface, and the coupling takes place on the metal surface, and most often of course all these ligand coupling or the cross couplings are referred to the transition metal catalyzed reactions, and there are again more than 10 different cross coupling reactions. What are these? Just quickly review. What are the names? There are 10 different names, right? What are the 10 different names? Okay, I mean so many, right? All of you know. No, but when I say so, but you are now in the higher class, you have to prioritize. Means which one is very good, which one is very bad, which one is okay. Yes, I think in my mind, Suzuki, because this morning I was going through a review article on patented literature on cross couplings. What I find that most of the examples are from the Suzuki couplings. Okay, so Suzuki coupling. Okay, and next most, which one you think? I would say Negishi. Next. Okay. Heck. Next. Okay, I'll take Sonogashira. How is that? Sonogashira. Okay, Stille. I would take still a little later, maybe Kumada. No, at least in this class I will take something else. Buchwald, Hartwig. Then I will take Stille. Anything else? Can you? Okay. There are other couplings actually people call actually Hiyama. Fine. Hiyama is yet to be developed. Okay. Who? Fukuyama. Okay. I don't remember, but I roughly remember. Do you remember what is it? Toru Fukuyama. Yes, I know. And then there is one more. Is Suji Trost coupling. And so I think there are many, of course there are many others, but these are the main ones. Now you have to know a little bit about this actually strength and weaknesses of these. Okay, all of us know they are all most of them, not all of them, most of them are transition metal catalyzed. Okay, and there are many more. There are quite a few, because alloy Fuchner also is associated with a discovery, and so that is very similar to Kumada reaction actually. We will talk about that little bit of this, but for example, Suzuki coupling, what are the disadvantages, let us say? What are the disadvantages of or weaknesses? What are the weaknesses of this Suzuki coupling? So okay, let us talk about the weaknesses. I think that strength, I think rest of the things are the strength. Suzuki coupling, okay. So what do you think Suzuki coupling? Suzuki coupling, basically the organoboranes are more expensive, that is it, nothing else, because many cases what you have to do, you have to convert these organolithium, organomagnesium, all these organometallics to organoboranes, or the direct borylations are very expensive. There are very few reagents. So that is basically the cost. Cost is important. Weaknesses. For Negishi coupling, Negishi coupling is, there are many strengths though. So, but is there any weakness of this Negishi coupling? Negishi coupling, the organozinc compounds are water sensitive. When a Suzuki coupling can be carried out in water, but Negishi coupling cannot be. Like organomagnesium compounds, similarly Kumada coupling for example, water sensitive and not that general, not general. So, these are the things. Okay. The Heck coupling is what are the weaknesses of the Heck coupling? It's very good. Huh? What is that? Heck coupling is Heck coupling involves sp3 and sp3, right? Oh, right, sp2 and sp2, right? No, weak coupling. That means sp3 cannot be done. Right. So, that means limited. So, the scope is limited, and so scope that means limited to sp2 carbons. So, that is okay. And one more, Heck coupling is good for intramolecular reaction, but Heck coupling also gives rise to regioisomers. It's regioisomers. If you have a double bonded compound, you can have addition in alpha position or beta positions. So, regiochemical problem. Sonogashira is good, is very good, but it is limited. Sonogashira it is limited to only certain kinds of, that means the scope is limited, that is it. And Buchwald reactions, of course, it is not really carbon-carbon, it is not really involving the carbon-carbon ligands. And if you recall, Buchwald reaction actually requires a nitrogen. That means let us say you have R something like this, R and H2, then that means this X would be removed. So, that means it is somewhat restricted, but it is very useful in heterocyclic compound, heterocyclic chemistry. And Stille, I mean there are so many plus points. Stille is very good for the total synthesis, and it is very mild reaction, very mild reactions, but expensive. And then disposal problem. I should say disposal problem is more important. Means Stille is in heavy metal, and disposing the tin in large quantity, that means it is not scalable. The scale of the reactions cannot be increased. Okay, so you get a lot of, so this is a disposal problem, waste. So, wastage of materials. Hiyama is not really into the chemical industry yet, but and this okay. So, and this is Suzuki and Trost coupling. This is somewhat separate, but again it is limited in scope. That means scope is limited, limited scope. What it means, it always requires an allylic kind of acetate, allylic compound, oxygenated allylic compounds. So, that means you have a limited scope in the reactions. Okay. So, that means, and for us, I think the first 2-3 reactions are very useful, or I should say 5. So, Suzuki, Negishi, Sonogashira and Kumada, and probably okay 1, 2, 3, 4, 5, 6. The first 6 should be very useful. Let us look at a look at an example from, let us say, again from the patented literature. The target molecule is a heterocyclic one, where it sort of looks like a biaryl. It is a pyrazine derivative, that means nitrogens are 1,4,1,4. Now, you have a substituent N-pentyl, and you have O-tert-butyl. So, grossly looking, it is a biaryl. Now, where do you connect them? Where disconnect them? Or disconnect it? obviously this is the aryl sp2 or sp2, all these transition metal conditions are very well suited for sp2 sp2 connections, right. So, if this is so, now you have to make a choice, that is the whole trouble. The choice should be, I mean, whether, and I mean, so you have, since you have so many possibilities, so many different kinds of the couplings, which one do you choose? Making a decision is important, or taking a decision is very important. So, to do so, you have to actually learn all of the reactions in depth, then only you can do it. Okay. In this case, so which one is this? Let us say you give me suggestions, I will try to defend you or rather myself also. So, that means two units are of this, right. This is one of these sorry. Now, you have to put groups here. So, you have to fill in the blanks. Well, so we made a mistake in the first place. Actually, the other possibility we have not looked at. Other possibilities could be this is also pentyl. That means, we can also think of, because at one point that connection between the sp2 and sp3 were tough. Now, I mean, there are, I mean, Suzuki, both Suzuki and Negishi are now well developed for making a CC bond between the sp2 and sp3. So, that means the options are wide open now. So, what can you do? So, this is also a possibility. Now, we are in the heterocyclic chemistry class, right. So, what do you know? We know in a heterocyclic molecule the two position is very reactive, especially have a nitrogen in 6-membered ring system, and that is what is done in the one of the choice is in the patented literature. The choice is that you first make this biaryl somehow, and biaryl, then you take this halogen up here, understood? Because all of us know that halogen in a next to nitrogen in a 6-membered ring is pretty labile because of this low electron density at the carbon. So, all sorts of nucleophilic addition, elimination reactions should take place. So, if this is the substrate, that means one side is now well chosen. So, what should be this is what I call this acceptor. Now, you have to have a donor. Right. What is the donor? And donor could be again this donor, if you just look at the periodic table, we have talked about lithium, then diagonally placed magnesium, then what we talked about, further lower down go to zinc. Is there anything before zinc? You had copper, right? Copper was in one position, right? Group 1. So, copper. So, that means up to copper we do not call actually this cross coupling reactions. So, the reactions of the copper reagents with this thing because they are not transition metal catalyzed. So, we have now zinc, then go to boron. No, palladium is a catalyst. So, it is not a reacting actually donor. Then comes aluminium. Yes, aluminium has limited use. I cannot ignore aluminium. And, no, silicon. Then germanium is out. Then tin. So, these are the very few metals actually. So, when you talk about the donor, you can concentrate on all of them. Sometimes, as I have said before, organolithiums can directly displace these halogens. Okay. Normally it does not work well, because you have now another nitrogen. So, it can cause all kinds of the problems. Okay. Magnesium also is very similar. Magnesium normally is less reactive. So, to make it a more reactive, now you know that there are all possible this transition metal catalyzed reactions. Although it is less reactive, now we know the cross coupling reactions, the Kumada reactions. So, you can think of the Kumada reaction. First, let us think of Kumada reaction. So, that means pentyl magnesium. In this example, they have used magnesium bromide. Okay. What next? You have to choose a right catalyst. What is the catalyst? Kumada actually, yes, originally used nickel catalyst, but many other people like Nakamura, Alloy Fusna, they have used iron. And in this example, in the patent literature, interestingly, very interestingly, they use catalytic amount of ferrous chloride, less expensive than commercially directly available ferrous chloride. Okay. And the yield is not mentioned, since it is in patented literature, and this was developed in 1984 by a company called Ube Industries. Okay. So, that means it is an industrially suitable reaction, very useful magnesium. And so, quickly then summarize what we talked about, and then you have to, that means you have the halogens etc. Again quickly. So, our first choice now in heterocyclic chemistry is Suzuki. So, you have to know the donor. What is the donor? Boron, right. So, boron, and acceptor, that is what also you have to think about, acceptor. What are the acceptors? Could be CX halogen. What else? What else? Trifluate, very good. Actually, in organic chemistry, such an important, such a vast subject, you can suggest anything. If not done, you can start doing it now, believe me. And recently I have seen, they have put carbon sulfur, sulfonium, ammonium salt, carbamate, all kinds of living groups, which has little bit of living group property. So, that means it is very difficult to actually evaluate ancestor scripts from higher classes. Anybody can just argue, sir, I have seen this article somewhere, this has been displaced by this. Okay, so versatile, but of course, now we have to, as I said, we have to prioritize. We have to, give more importance to one to the other, in preference to the others. Okay, so this is the thing. Then catalyst. So, catalyst, all of us know Suzuki means often is the palladium, and then so it goes to Suzuki. Then is Negishi. Negishi primarily it is carbon zinc. So, this is, and the acceptors are all same, acceptors of carbon zinc. Occasionally it is carbon aluminum. In fact, in older industry, some of the reactions were carried out with aluminum, and so then palladium. Then if someone says, okay, nickel, well, then I have to say, well, might be, but most commonly is palladium. Okay. When I say palladium, means palladium 0 and many more catalysts. Okay. And then what is our next choice? Heck. Heck, what is the donor? What is the donor? Carbon. What is the donor? No, donor part. The donor part means the substrate that would donate these alkyl groups or aryl groups. In Heck reaction, carbon hydrogen, sp2, carbon hydrogen, alkene. So that means carbon hydrogen of alkene or even arenes. Simple benzene also would do the reactions. Okay. And acceptor again same thing. Accept anything else? One more. As this diazonium salts. Diazonium salts are very useful, and again it has it is also a name reaction, something like called Matsuda or something. Heck Matsuda reactions. Only difference that in this case the acceptor is this. We have done it. In fact, our reference has appeared in Smith's book. Okay. So, because we have used a Heck reaction of the diazonium salt in the synthesis of an aryl moiety. So, and this is very useful. You just can just go through this written literature. You will find plenty of references. In fact, there is an article, review article also on this, and many a time. In fact, the once we did actually this reaction has been partly developed by one ex faculty of Jadavpur University, Soumitra Sengupta. He has left the university. He is now in industry. He did this reaction in water, and in one of the papers also he describes you do not need palladium, very expensive palladium, just palladium charcoal that is used for hydrogenation, that can also be used. And I think we did once, that works well. Okay. So, that is the reason why this reaction now is named after the corresponding scientist Matsuda or something like that. So again it is a palladium. For the boron, I think you have to know a little bit of these Suzuki couplings here. This boron can be used as a boronic acid derivative, and then or this is one of the commonest one, and other one is boron, that pinacol derivative. These days lot of people are using actually the corresponding pinacol derivative, and I think Hiyama we will not talk about, and other thing. And then I think in heterocyclic chemistry that is most important is also Buchwald reactions and Sonogashira. These are the two. Okay. So, in Buchwald, what is the donor? Donor is amine. So, carbon, nitrogen, that means amine NH. So, amine so nitrogen, or you can write nitrogen, amine is the donor. Acceptors again halogens and triflet most commonly. Okay. Sonogashira, what is the donor? Sonogashira, what is the donor? Is the corresponding acetylene compounds. That is it. So, these are the I think I will not overburden you other things, but these are the things I think I should say 1, 2, 3, 4, 5. These 5 reactions are very useful in heterocyclic chemistry. Okay. And let us look at one of the I think all of you know the mechanism, or should I talk about the mechanism? I think what is the working out, what is the mechanism? Let us say Rita, what is the mechanism? What are the steps? Let us say working mechanism. No detailed mechanisms. Okay. Detailed mechanism will consist of 6 different steps, right? 6 different steps: oxidative addition, and then no, oxidative addition, isomerization, cis-trans isomerizations, the ligand cis-trans isomerization, then insertion, then migration, so many things. Okay. So, that means you can actually a reaction mechanism can be divided into 3, 4 I mean more than around 6 different steps. Okay. But in organic those are the approaches taken up by the organometallic chemist. For organic chemist I think 2-3 steps are enough. One is this oxidative addition, then oxidative addition, then I think I would say transmetallation maybe, or you can say insertion whichever you like, and then reductive elimination. That is enough. Okay. So, I do not have to tell them. Now, there are few tricky things you have to remember. If you will, let us say, if you go for the Heck reactions, you will see something different. I mean, sometimes the outcome is not really as expected. For example, I have a reaction which I write now. This is a triplet, and then you have enamine, and the reaction conditions, that you have to sometimes you have to be a little bit careful about these reaction conditions. In this case, palladium 0 with the one I have here is R binap, this is only 3 mole percent, and there is an amine, there is a cyclic amine. Okay. So, all of us know this binap, R binap means basically to introduce this chirality in the final product, and binaphthol phosphines. This amines normally are given. Thus, you have to I think understand what is the use of amine. What is the use of amine? These are the things you have to just take note of. Then in a reaction of this kind, you have to have the right catalyst, you have to write additives also, and many times you will see in Heck reaction, especially in Professor Jekarai's lab, they often use a base that is not commonly used. What is it, Moon? Okay. So, okay, what about no senior research scholars? Okay. They do not use the normal base like sodium carbonate, sodium bicarbonate or triethylamine. They use something little expensive. That means, some of the reactions are very tricky and sensitive to the reaction conditions, and cesium carbonate. Okay. So, likewise you see here is particularly base, but base is required. What is the purpose of the base? In most cases you are eliminating as a net result like say HBr or HI, all these things. Okay. So, to compensate that, and occasionally base is also like triethylamines, triphenyl phosphines, they are used to reduce the palladium to palladium 0. So, fine. So, now what is the predicted product so it should be a what is the class of the reaction? The reaction should be categorized as follow. What is the reaction? Heck reaction. So, Heck donor is this is olefin here and this. The product that you will find. So, product what you will find is an ester group again, and this comes from the triplet, and double bond is now moved. To the other side. Normally, it gives Heck reaction gives alkene. That means alkynyl hydrogen is substituted. Alkynyl, that means we would have expected the reactions on this side, this right with conjugated double bond. But what you see here is a deconjugated double bond, primarily because of a step in Heck reactions. Although we have worked out this simple working mechanism like these oxidative eliminations, but there is a critical step also in Heck reaction. What is that critical step which will account for this sort of isomeric compound? Actually intermediate CO2 Oh, okay. No, okay, CO280 right here. So, the intermediate actually the palladium is somewhere here. So, you have these double bonded ester here, and this is ester and this, right. And what is that next? Beta elimination, that is the thing you have to remember. So, that means a beta elimination takes place. So, beta elimination takes place here. So, all of us know these are the things you have to recall. So, once you have this beta elimination, so you will have beta eliminations, and so you will get these, and this is OMe. What next? The same thing will undergo isomerizations. Again polarization will take place on the other side, and eventually it will go to the double bond, simply because you have nitrogen. The nitrogen lone pair would assist the stabilization of the double bond. It is an enamine structure. Enamine structure.
So it has the possibility of forming double bond isomerizing both ways.
Isomerizing both ways, right? There is a possibility, but the product will go to the more stable ones. Right. Okay. So, this is somewhat common also. Let me give you one more example from the 5-member heterocycle. You have a dihydrofuran and a triplet like this. So, a triplet do this reaction. In this case, palladium palladium DBA dibenzyl acetone, palladium DBA, this is only 3 more percent. Mind it, the percentage requirement of the catalyst is very little, and so then diisopropyl ethyl amine, and the temperature is only 30 degree, means sort of like room temperature, and again a base is required, amine base. This is known as, this is also sometimes people say unique base. Okay. And of course, anything else is missing? Anything missing? Solvent benzene, and a ligand, phosphorus ligand. Okay. So, the phosphorus ligand in this case is a diphenyl phosphinobenzene kind of molecules, and once again is also in heterocycle, it is a chiral heterocycle. It comes oxazolene heterocycle. And this is for introducing the chiral center. So, the product here would be this is this acceptor part, and the donor part now again a furan. Now, see the double bond has undergone migration to this next thing. So, like this, that means it is not Heck reactions. Sometimes it is predictable, sometimes it is not, but it once it works, it gives the well defined the structure. I think maybe one more. Okay, I think I will stop here. We will stop here. In next class, basically what we will do, we will have more examples. First, we will restrict the examples to the 5-member ring systems and try to see what are the functional groups that could be accommodated, and then we will see some of the things like total synthesis done. And before I end, let me give you just a little homework to do at home and see if you can do it. How to produce this. Okay. and one more. Is that all right? So, we will actually discuss all these things next class, but before that you just work out. In fact, this is a very interesting one. This is again a recent example in one of the papers. This just